Hello, everybody. For our last thought in the second semester, before we get into review, we do have to go over constructions, just as we did at the end of the first semester. So we have 6 of them to consider from things we've seen throughout the last few months here. The first one here in the notes, we're looking how we can construct a perpendicular line through some given point. So imagine we have some line somewhere, and we want to construct a perpendicular that goes through that particular point above it. We're going to need to create a little bit in this picture before we can actually construct it. So we'll use the point we're trying to pass through as the center of an arc, or in the case of how Desmos always draws it, a circle. And then we're going to find the perpendicular bisector of this segment that's been created by the 2 points that it crossed. That way it's guaranteed to be perpendicular to the line and simultaneously pass through the point up above it. And if you don't remember the perpendicular bisector, it's 2 circles, one starting at each end of the intersection, and then draw the line that passes through them. Let me hide the circle part so that it's a little easier to see, but what you've created is a line passing through this dot, and if we grab the angle measurement, we can confirm that it is in fact perpendicular, an exact 90-degree angle. For the next one, we're looking at how to build a square given some segment. So let's consider that we have this line here, assuming this line segment, and we want to build a square off of it. We have to actually go through the properties of a square real quick. Square needs 4 sides that are congruent to each other, so we need them all to be the same length, and at the same time it needs 4 right angles. They all have to be perpendicular to each other. So the easiest way to achieve this is to do the same perpendicular bisector kind of discussion that we just did in the last one. So let's actually pick one end to create my circle. And as the note says, extend this into being the diameter. So that way it goes all the way across. The idea is I want to do the perpendicular bisector of this diameter because it's going to create a line that's 90-degree angle and goes out here to be the same length because it'll be the radius of the circle too. So the same perpendicular bisector creation will go from one end to the other and back, and we will drop the line that passes through them. Now, realistically, the only part that I care about is from my original point to the edge of the circle. The rest of everything can go away, but here's what you've created. Since it's perpendicular, you know you have a 90-degree angle here, and simultaneously, these 2 lines are the radius of that first original circle. So you know they're the same length. You've created half of your square. The only thing left to do is very literally do it again, but this time go do it on the other side of the picture. That way it creates one over here instead. So let's hide all of that. Oops, missed a couple of dots. So we'll hide those. And now I got to do the same thing over here. I want to create this portion of the square because then at that point, all I got to do is close the picture and I'm done. So we're going to repeat that entire procedure just off the other dot. So we'll do it off of this one now. So here's a circle. We'll extend it into a diameter. I will find the perpendicular bisector of this diameter. I will drop a line through it so that I know where it is, at which point I know where the part of my square is. Here's another right angle, and from here to here is the radius of the circle, just like from here to here was. So I now have 3 sides of my circle. I just need to hide all of this stuff again. That way it's a little easier to see. So we'll click on all of them and hide them since we don't actually need them for anything other than to find that line. The last side of the square is the obvious one. You have 3 sides of a square. The 4th one is just connect the last 2 dots. You know, this was the original segment that was given. We built a perpendicular of the same length, a perpendicular of the same length, and then close the picture out. You've created a perfect square based off that segment that was given. For our third one, we're going to shift over to the circles chapter, and we're going to look at how do we actually create a tangent line for a circle. So given some circle, how do we create a tangent line that passes through it? The easiest way to do that is to use the dot that's on the circle as the center of some second one. So let's just create a second one, say there. If I do the diameter of this circle and find its perpendicular bisector, I'm guaranteed it's perpendicular and it passes through this point, which will make it tangent to the original circle. It's a very quickie construction. So first things first, we need the diameter passing through. So we'll have that. Now let's go do perpendicular bisector. This is going to be the same construction that's used in almost all of these. It's one of the most important ones to ever learn. So we'll go from one end of the diameter to the other and back. And we will drop a line through those two. Let's hide our circles because the circle parts we don't need. We constructed the perpendicular bisector. These we don't need for the discussion. What we need is here's the original circle and here is a line that we know is perpendicular passing through the outside of it. If it's perpendicular to the radius of the circle, by definition, it has to be a tangent line, which you can even look at it. This line does not touch the circle anywhere except at this point right on the outside edge of it. The last three that we have also deal with circles, but they deal with how do we construct figures from them. So we're going to build other pictures from the circle concept. So the first one is how do I build an equilateral triangle? So given some segment, say there to there, how do I build a triangle that is exactly 3 copies of that segment? Well, luckily, the perpendicular bisector construction strikes again. If we build the perpendicular bisector, and then we simply use either the top or the bottom, either point's the same. The argument's the same either way. The claim is that that is now an equilateral triangle. The proof of it is really easy. This line that was originally given is the radius for the left circle and is also the radius for the right circle at the same time. So you know these two circles are exactly the same, which means this point up to here now matches this one down to here because they are literally radius of the same size circle. If all 3 sides are the same, we call the triangle equilateral. It's a very quick construction. Doesn't take too much effort to create that one. But we're going to use the same concept for that to generate the square and the regular hexagon as the last 2 here. So same idea, given some circle, we want to build a square on the inside of it. So how do we guarantee that we find exactly 4 points on the circle that are going to create 4 congruent sides and 4 perpendiculars for 4 right angles? The easiest way is to use the properties of a square. We know the diagonals of a square have to be congruent, and it's easy to create congruent lengths inside of a circle, radius, diameter, and so on. And we know they have to be perpendicular, and as we've done in every single one so far, perpendicular bisector will guarantee my perpendicular. So we are going to do exactly that. Here we'll take a diameter. This is going to be one diagonal of my square. I need a perpendicular to it that is the exact same length. So if we create the perpendicular bisector, we're going to generate a diameter that goes from here to here, and it's going to be the exact same length because it's the diameter of the circle. That's the exact plan. So again, perpendicular bisector for the 5th time in a row. It is the fundamental construction concept. We'll go from one, whoops, that was my fault. I clicked too early. One side all the way to the other and back. And we will drop the line through that intersection. But realistically, let me draw a segment. I actually care about this one to here. I only care about how far it is in my original circle. So the 2 big ones we can go hide now because all we needed them for was to create this line. If I hide all of those, what I actually care about, oops, I forgot to put the segment the first time. So from there to there. What I really care about is these two segments are both diameters, so we know they're the same length, they are congruent. And because it was built from the perpendicular bisector construction, I know they form right angles. If I want to inscribe my square, all I have to do is connect the 4 dots. I have found 4 points that are going to generate a perfect 4-sided square, perpendicular, everything. So if you want to see it clearer, we can always hide the 2 diagonals that we use to generate it, but it is a square perfectly inscribed inside of a circle. We do the exact same thing for the regular hexagon, just we need 6 dots instead of 4. Obviously, a hexagon has 6 corners and 6 sides, but it's the same exact logic. We are going to do the exact same construction again. So given some square, which means some circle, we want to go generate the 6 points that will create a hexagon. Well, the first 2 we'll know right off the bat. Let's put the diameter in, and I've already found my second one, these 2 points. So now I need to find one up here and one up here, as well as one down here and one down here. I just need to find exactly where they should be so that I can create that. If you read the direction, it says point blank, use the equilateral triangle construction. We're going to do the equilateral triangle construction for the left radius, and then we'll do it again for the right one, because it's going to create a point above and a point below, and then again, a point above and a point below. It's going to be perfect alignment. So let's do the left one real quick. And we'll go back. I don't really need to draw the line. All I care about is the dot. The one there will make an equilateral triangle above, which means now this is the same length. If I do the same one down here, I have the 2 points here. Let's just hide our circle because we don't need it for anything. Repeat on the other side. We'll go from there to there and back. At which point I have 2 dots. One here from the perpendicular bisector and one here from the perpendicular bisector. We'll hide our second circle, at which point I now have 6 points. All that remains is to go connect the dots. If I connect this one, I know this is the same length as this because I have an equilateral triangle here in this spot. If I go here, I have an equilateral triangle in this spot, and they both use this radius. So I know these 2 are the same length. If I go from here to here and here to here, I know these 2 are the same length because they share this radius, at which point now all that remains is connecting these 2, but that's the equilateral triangle that's here. So this one matches the other ones because it's already part of it, and the same argument for the one at the top. You have created a perfectly equilateral regular hexagon all the way around, guaranteed. Excuse me. That's everything for the constructions out of semester 2. You'll find the assignment is a couple of multiple choice questions that ask you what's being built because it's partially done, or somebody was building this, but they made a mistake. What was it? Things like that, just like it was in the first semester, at which point you should be good to go and do that assignment. If you've got any questions, make sure to ask your teacher, and good luck on the end of course exam when it comes up, because that is the only thing remaining in the class.